So welcome to the course APL 100. My name is Savan Sinha and I am a professor in the Department of Applied Mechanics at IIT Delhi. This course is comprised of 42 hours of lectures, and then there are 14 hours of tutorial sessions. We start with lecture 1 today, and in the beginning I have some definitions, very basic definitions. Some of you might be aware of these definitions already. In that case, it will be a review. And for some of you, some definitions may be new. And these definitions will form the basis on which we will build the concepts required to be learnt in this course. The first definition is of a particle. What is a particle? A particle is a point mass. Now, point mass, mind you, has no sense of orientation. It has no dimension either. A point mass has no length, breadth or height, and it has no sense of orientation. What I mean by sense of orientation, if you focus on this pen, this is not a point mass. It has a sense of orientation in the sense that if I am the observer, right now I say that the tip of the pen is pointing upwards. At a later time instant, the tip of the pen may be pointing rightwards. So it is the same pen, but I would say the orientation of the pen has changed while I observed it. This is what I mean by change in orientation. Coming back to a particle, since it has no dimensions, it does not have any sense of orientation. The next definition is of a body. A body is defined as a continuous distribution of particles with some interparticle binding forces. And because of those interparticle binding forces, this bunch of particles or this distribution of particles tend to move together as we perceive. The particles of a body are not completely independent of each other. Once we have the idea of a body, we distinguish between two types of bodies. First is a rigid body and the other is a deformable body. A rigid body is defined as a body wherein all interparticle distances remain unchanged at all times. I repeat, a rigid body is defined as a body wherein all interparticle distances remain unchanged at all times. Whereas a deformable body is a non-rigid body. You can also call a deformable body as a non-rigid body. And in a non-rigid body, some or all of the interparticle distances may change with time. Okay. I have drawn a diagram here where I am showing a rigid body, and in that rigid body, suppose we identify 4 points, point O, point B, point A and point D, such that the line segments connecting O to the other 3 points A, B and D are mutually perpendicular. If the body is rigid, you would observe that the distance between OA, distance between OB and distance between OD will remain unchanged. I am not saying distance between OA is same as distance between OB, no. But whatever is the distance between O and A will remain unchanged at all times. Similarly, the distance between O and B, whatever it is, will remain unchanged at all times. Not only that, in a rigid body, the angle between the segments OA and OB, for example, will remain unchanged at all times. If initially the angle between OA and OB was 90 degree, it will remain the same at all times. And same goes for the other angles BOD and DOA. These observations follow from the definition of rigid body, the way I defined here. Whereas in a deformable body, I have shown again a pair of cartoons here. The body may look like this, like an ellipsoid at time t, and at time t plus delta t it may become a flatter ellipsoid. And I hope you will agree, looking at this crude picture itself, that if you consider 2 points on this body, the distance may change from t to t plus delta t. And again, if you consider 3 points and focus on the angle that exists between OA and OB, that angle may also change at different time instance. Now, a solid body can be a rigid body or a deformable body, right? There are primarily 3 states of matter: solid, fluids, solids, liquids, and gases. A solid object can be a rigid body, or maybe it may be a deformable body. Whereas liquids and gases, if you focus on a chunk of liquid or a chunk of gas, we can call that as a liquid body or a gaseous body. Such bodies, liquid bodies or gaseous bodies, are always deformable. Right? In this course, the course name is Engineering Mechanics, and we focus entirely on the mechanics of particles and mechanics of rigid bodies. So there will be no reference to liquids, no reference to gases in this course. Only solids and rigid bodies. We also, as engineers, we also want to study mechanics of non-rigid bodies. Indeed, many branches of engineering, they introduce their students in the second year of their BTech program to mechanics of deformable bodies. In IIT, we have a course on mechanics of fluids. Fluid is a deformable body. There you study how fluids, study mechanics of fluids. And then there is another course which is called mechanics of solids. Now, when you say mechanics of solids, what we actually mean is mechanics of deformable solids. Whereas when we say engineering mechanics, at least in IIT Delhi, when we say engineering mechanics, we mean study of mechanics of particles and rigid bodies. I hope these distinction in the choices of the words and adjectives is making sense and it is clear to you. Moving on, more definition. Kinematics. Kinematics is the study of motion or of a particle or a system of particles without any reference to the cause of motion. So when I say motion of a particle or system of particles, what I mean is studying displacement of a particle, trajectory of a particle. right? Trajectory means path followed by a particle. We also talk about velocity and acceleration of particles. So all this study without worrying about the forces that cause the motion is called kinematics. Whereas kinetics is the study of motion of a particle or a system of particles along with the cause of motion. So you also study forces, the relationships that exist between the forces that act on a body or a particle and how that force translates into the motion of the particle or the body. That is kinetics. In some books, kinetics is also called dynamics. Finally, there is a field of study in our context which is called statics. Statics is the study of a particle or a system of particles at rest. Now you may wonder, if the particle or a system of particle is already at rest, what do we study? It is at rest. Why do we worry? Now, it does happen many times that a particle or a system of particle is at rest even when a set of forces is acting on that. A set of forces is acting on that. It's not a trivial situation. A trivial situation is body is at rest, no forces acting. That situation we don't worry about. But then, and I call this a trivial situation. There is nothing more to infer. There is nothing more to examine. However, there are situations in which you have a body which is at rest, but it is at rest under the action of a set of forces. So this branch of statics tries to understand the relationship that exists between various forces that are acting on the body, and yet the body is at rest. This is of interest to us. Alright? Combining all these three fields of study, kinematics, kinetics and statics, we put together in a basket and call that basket as mechanics. So in this course, we are going to study kinematics, kinetics and statics of particles and rigid bodies. As far as our time investment is concerned in this course, statics is tentatively 20% of the time we will give to statics, whereas 80% of the time will be more or less equally distributed between kinetics and kinematics. More definitions. A reference frame. What is a reference frame? A reference frame is a set of locations in space such that the distance between every pair of location remains the same at all time instants. I repeat, a reference frame is a set of locations in space such that the distance between every pair of locations remains the same at all time instants. Now, if you compare the definition of a reference frame to the definition of a rigid body that I mentioned 2 slides ago, you would observe that the definition of the two definitions are very similar. A rigid body is defined as a body wherein all interparticle distances remain unchanged at all times. Whereas I'm saying a reference frame is a set of locations in space such that the distance between every pair of location remains the same at all time instants. Now, if you follow these two definitions, it turns out that every rigid body, if you have a rigid body, you can consider that as a reference frame itself. Every rigid body qualifies to be called a reference frame. Now, why do we worry about calling a rigid body a reference frame? Why do we worry about even thinking or conceptualizing the idea of a reference frame? Right? You may wonder. Now, rigid body is something very tangible. So defining it was making sense. This is a rigid body, remote control. This is a mouse, this is also a rigid body. These are all tangible things. The concept of reference frame, however, seems to be dropping from blue sky. And you may wonder, why do I need a definition of, why do I need to define a reference frame? Now mind you, a reference frame is required to perceive and describe the motion of a particle or system of particles. Motion is always perceived with respect to a reference frame. A reference frame provides the contrast, the background against which motion is perceived by human beings. You think about it. You are standing in a park and there is a bird flying. Now think about this. Your mind is interpreting the bird to be flying because there is something in the background which doesn't move at all as you perceive. Right? There are trees, there are houses on the ground which are all fixed. Your mind is observing that contrast. Your mind is conscious of that contrast. And against that contrast, in that background, there is a bird that seems to be changing its position. At one time instant, it is near tree A, and at another time instant, it goes to tree B. Whereas tree A and tree B have not moved as interpreted by your brain. So for your mind to conclude that the bird is flying, you need something which is stationary in the background. That stationary thing is what we call as a reference frame. A reference frame can be visualized as a human observer fixed to a rigid body. Think about this. When you were observing a bird in the park and you reported that the bird is flying, the reference frame was you being tied to a background, you being tied to a rigid body which is nothing but our Mother Earth. So Earth deemed as a rigid body and you as human observer firmly tied to it. They make the reference frame, and with that, with respect to that reference frame, motion of particles or a system of particles can be observed. Right? To visualize it a little bit more clearly, I have drawn a cartoon here. So you have a rigid body which is like Earth, and then this is you, a human observer. Imagine yourself completely tied with the Earth. You are not moving with respect to Earth. Then this pair of eyes, your eyes and the background, they make a reference frame. Right? Now once you have the idea of a reference frame, one must also realize that motion, the perceived motion, is frame dependent of the same object. The same object, the bird. If you are observing this bird whilst being tied to the earth, you say that the bird is flying horizontally in a straight line. Suppose you go to the moon. There is your one of your friends goes to the moon. He sits there. Simultaneously, he is observing the bird, maybe through a telescope. By some means, he is able to observe the same bird from the moon. What kind of motion he would report? Will he report a straight line motion? Maybe not. To him, the bird may be following a curved motion. Right? Motion is frame dependent. To consolidate this concept more, I have another example shown on the slide. I have this ground frame which I am calling as RB2 or rigid body 2. Rigid body reference frame synonymous. There is an observer tied to rigid body 2 which is ground. And then imagine there is a disk. There is a disk which is rotating with respect to RB2. Like in an amusement park, you may have a disk which is rotating. I call that disk as RB1. And suppose your friend is sitting on that disk in the amusement park, and your friend is completely tied to the disk. So your friend tied to disk or RB1 is reference frame 1. You tied to the ground or rigid body 2 make reference frame 2. Right? So we have two reference frames now, and then we focus on a particle called P, which is fixed to the disk. It is a material point on the disk, and this is the symbol I use and I will continue to use in my course to denote that this particle is a material point of RB1. P is a material point or a fixed point to rigid body 1. So we have two reference frames and one particle. I asked the question, what is the motion of P? Is that a complete question? No, the question is not complete, because there is no unique answer to this incomplete question. What is the motion of P? Not adequate. You should ask, what is the motion of P with respect to, say, RB1? Then I can answer the question. Similarly, you can ask the question, what is the motion of P with respect to RB2? Then I can answer the question. And I hope all of you can visualize this situation and answer the two simple questions. What is the motion of P with respect to RB1? The answer is no motion. For your friend who is sitting on the amusement park, for whom the contrast is the disk itself, particle P does not go anywhere. Its distance, its direction, where it is located, remain unchanged as observed by your friend. And that's why I will say that motion of P with respect to RB1 is not there. There is no motion. However, the same particle P, if I ask the question, what is the motion of P with respect to RB2? The answer will be affirmative. The answer will be yes, there is motion. Now, how do we describe that motion? We will look at that later. At this point, I am only looking for an yes or no answer. For RB2, for you who is sitting on the ground, being tied to the ground, yes, P is executing a motion. If I go ahead and ask a question, what kind of motion? I mean to say, can you describe the trajectory of P as seen by RB2, as seen with respect to RB2, or as seen by you? You will say that P is following a circular motion in a horizontal plane. Whereas your friend, what is the trajectory of P for your friend? There is no trajectory. For your friend, P is just a particle and it remains without motion. It just remains as a point. The trajectory is a point, that's all. Which in other words means to say that P is not moving. So motion is frame dependent, and that again underlines the importance of having defined, having conceptualized, having absorbed and understood and accepted with open heart that we need to have a reference frame to describe motion of a particle or a system of particles. Now, building on this concept of the fact that motion is frame dependent, let us now talk about rate of change of a vector. Now, in this course, we will use an underline to denote a vector. Many books, when we denote a vector, we put an arrow or a bar on the top of the symbol. Fine, that is okay. but it is just my habit that I put an underbar to denote a vector. And I would request you all to be clear about it as I move to newer and newer topics, that an underline will denote a vector. So the question I am asking, if I have a vector, how do we find rate of change of vector, and what is its significance vis-a-vis reference frames that we talked about? I go back to the same situation. You are being tied to the ground, RB2, reference frame 2. Your friend sitting on a desk in an amusement park. Your friend being tied firmly to the desk there, which we call as RB1. Now let me define a vector. What is the vector? The vector is the position vector of P measured from this point C. So C is the center of the disk and P is a particle fixed to the disk. I draw a line segment connecting C to P, and that line segment I am calling as a vector. Why vector? Because it has distance and since it is a line, it can have different directions while still having the same magnitude, and that's why I denote this vector as, this is how I define my vector. Now let the distance between C and P to be 1. For simplicity, let the distance be 1. So distance is going to remain constant. I want to ask the question, what is the rate of change of E cap with respect to RB1? Now E is a vector, so a vector can be perceived to be changing because of two reasons. Either its magnitude is changing, then also we will say that the vector has changed, or its direction changes, and again I will say that the vector is changing because of that. In general, both magnitude and directions can change, and still we will say that the vector has changed. However, in my case, the vector is a unit vector, so the only reason why it will change is if I perceive its direction to be changing. I hope you agree with me. E hat will be reported to be changing only when its direction changes. Magnitude remains constant. So my first question is rate of change of E as observed by your friend. In other words, the rate of change of E with respect to RB1. What is that? I expect all of you to visualize this scenario and tell me the answer. I hope most of you will be able to realize this now, right now as I speak, that the rate of change of vector E hat with respect to RB1 is 0. What I mean by with respect to RB1 is as observed by your friend. It is just a more technical way of saying rate of change of E hat as observed by your friend on the amusement tied to RB1 is same as saying the rate of change of E hat with respect to RB1. Okay? This quantity is going to be 0. Similarly, I can ask the other question, what is the rate of change of E hat as observed by you yourself who is tied to the ground? I hope you will be able to visualize and tell me that the rate of change of that rate of change as observed by you will be non-zero. Why? Because the vector is right now at this instant maybe going from, for you, maybe going from left to right. After some time, the vector may be pointing away from you. Clearly the direction has changed, and thus you will say, raise your hand and say, the vector has changed, and that's why this quantity should be not equal to 0. What does it imply? This simple example is telling us that rate of change of vector is frame dependent. Rate of change of vector is frame dependent. We will use these symbols to make it clear to the reader, to the listener, that if we are talking about rate of change of a vector, it is with respect to which frame? RB1, RB2. These subscripts are required. If you don't put the subscripts, your quantity is not well defined. So rate of change of vector is frame dependent. Once I realize this, I become curious that while the rate of change of a vector is frame dependent, how about the rate of change of a scalar? Is it frame dependent? Now this is my answer. Suppose I define phi as the distance between location of P and C. Alright? And now imagine that P is not a point fixed to the disk. Okay? P is an insect that is walking, crawling on the disk with its own mind. Okay? So now if you talk about the vector Cp, it can change its magnitude and it can change its direction also. So that vector will definitely be frame dependent. But if I would not worry about in what direction the insect is, I just worry about the distance between the center of the disk and wherever the insect is at a current instant. If I just focus on the distance, then it is just a scalar, right? Phi is the distance between the current location of P and C. Now we can define rate of change of the scalar also, and that definition will be following the definition from calculus. This is what I have written here. Now it turns out the rate of change of phi, the way I have defined, the rate of change of a given scalar, once you define a scalar, the rate of change of that is frame independent. I am repeating. For a given scalar, once you have defined a scalar and then you try to track the rate of change of a scalar, that is not frame dependent. It is frame independent. And that is why when we write in the language of calculus d phi dt as the rate of change of a scalar, there is no requirement to put RB1 or RB2. If you insist, you can put RB1 and RB2, but be sure that if the scalar is the same being observed from RB1, RB2, both will observe the same rate of change. So it is not required actually to put RB1 and RB2. In conclusion, rate of change of a vector is frame dependent quantity, and that's why you should put these subscripts, whereas rate of change of a given scalar is frame independent. So still sticking to the same example of P being an insect, having its own mind and walking on the disk, I can write the displacement vector of this particle or insect measured from C as in general as phi times E hat. Now, if I want to know the rate of change of Q with respect to RB1, this is what it will be, what I have written here. You apply product rule of differentiation, you get two terms. First involves rate of change of phi, the scalar itself. The second involves rate of change of the vector. And since the observer is on RB1, E hat does not change, and that goes to 0. So for your friend, the rate of change of displacement vector of the insect is going to be simply phi dot E hat, where phi dot means d phi dt, and that itself is frame independent. But the whole quantity phi dot times E hat is the rate of change of this vector, displacement vector, as observed from RB1. Now keeping the vector the same, that is q hat, under bar, I raise the question, what is the rate of change of q as observed as observed by u, who is sitting on RB2? For that we will start with this expression, apply product rule of differentiation, and then we observe that the second term, which involves rate of change of E hat with time, but here it is with respect to RB2, does not vanish. And that's why you will have two non-zero terms in general, which when added together will give you the rate of change of Q vector as observed by as observed with respect to RB2. So I hope this example gives you the clarity between how the rate of change of a vector depends on the reference frames in context, whereas the rate of change of the scalar part of the vector does not depend on reference frame. Now moving on, we define more quantities. Gradually we are building more concepts on the ones that we have already learned with increasing order of complexity, right? Let's define a quantity called velocity of a particle with respect to a frame F. So I have a frame F, I have a particle P, and I want to know what is the velocity, or I want to define what is the velocity of a particle, that particle with respect to frame F. In this course we will use this notation, V subscript P bar F. This is the notation. So this notation itself is conveying a lot of things. V means velocity, P means of the particle, and F means with respect to which frame. Now whenever I write VPF in this course, P will always be a particle, it cannot be a frame. Whereas F, where F is written on the right side of that bar, that has to be a frame. If you write Vp bar Q, where Q is a point, it has no meaning. It has no meaning. At least in this course, it has no meaning. Velocity is not of a point with respect to another point. Velocity is always of a point with respect to a frame. Please keep in mind. And also, whatever notation I am discussing, whatever notations I am showing, you have to follow that. I know there are different books following different notations, and I am not stopping you to read all those books. You read as many books as you want. However, keep in mind that when you solve a problem in this course, and when you solve a problem especially on exams or tests, I am going to recognize only one notation. That is what I am going to, this is what I am describing here. You simply cannot use a notation different from what I am telling you. If you use, I am not going to evaluate your work. If you use a different notation, I am not going to evaluate your work. Now in your mind, according to your exotic notation, the solution may all be correct, but I am not going to spend my time trying to interpret what your notations mean and what is the relationship of your notation to my notation, what I have in the class. Okay, so you read as many books, but you must follow the notation that I am talking about here. And this notation is the same notation that our textbook Engineering Mechanics by Dumir and Veeravalli follows. Alright, so how do we define VPF? That is the question. So we consider a reference frame, right? We consider a reference frame here, which I am calling as F. And then on F, I choose a point O, where O belongs to F. The way I am going to use O to define VPF is as shown on the figure. At time t, the particle is at this location where the cursor is. I draw a vector, displacement vector going from O to P. I call that RPO at time t. So I am using O as the reference point from where I will measure the position vector of a point of interest. That point of interest right now is P. Again, while writing the position vector of P, I have used a notation, and again you have to stick to this notation. RPO means position vector of a particle P measured from O. So when I use R, there are two letters associated or two characters in the subscript. First character is of the particle or the point of which you are measuring the location, and the second character represents the point of reference from where this vector is drawn. It has to be like that all the time. Now mind you, following our own notation, ROP will become simply as minus RPO, completely consistent. There will be a minus sign. ROP is not equal to RPO. Okay. Now I define VPF as what I have written here. It is the limiting value of this quantity in the limit delta t going to 0. So in the numerator I have RPO at t plus delta t and minus RPO at t. So it is basically the small displacement the point P has undergone between time t and t plus delta t as observed by who? As observed by this observer. We divide it by delta t and we let the limit to go to 0. That is what VPF is. That is the definition of VPF as observed with respect to F. Now suppose I define a similar looking quantity V prime PF. Look at this expression. How is V prime PF different from VPF? Mathematically, asking mathematically, how is it different? I have chosen a different origin to measure displacement position vectors of point P at two time instants. I have chosen another point as the origin, O prime, but still O prime is also a point fixed to F. Okay. My question is, if I choose the origin to be O prime and not O, will VPF be same as V prime PF or not? If it is not, then we cannot define VPF without describing where the origin is. But if these two quantities are same, then we can say that the origin doesn't matter. You need to choose an origin to measure position vectors. But as long as that point O or O prime is fixed to F, we are fine. The particle still has a unique velocity vector with respect to F. So are these two quantities the same? The answer is yes, they are the same, and I will show you the proof. What is the proof? The proof is here. So I begin with V prime Pf, which I defined like this, right? And then look at this diagram again. I am going to write, somehow I want to replace Rpo prime at time t. I'm talking about the situation at time t only. At this time instant, can I write Rpo prime vector in terms of Rpo and Roo prime vector? Can I do that? I repeat the question. Can I write at this time instant, time t, the vector Rpo prime in terms of Rpo and Roo prime? Can I write that? The answer is yes. This is the relationship. Rpo prime at time t is equal to Rpo at time t plus Roo prime at time t. Simple geometry. Comes directly from the geometry of the points P, or the locations where point P, O and O prime are, right? If I can write this expression for time t, I can as well write this similar expression for time t plus delta t. So Rpo prime at t plus delta t will be Rpo t plus delta t plus Roo prime t plus delta t, right? So now what I'm going to do is I am going to substitute Rpo prime in terms of this quantity, and Rpo prime again, Rpo prime at t plus delta t in terms of what I have here, and I'm going to replace Rpo prime at t in terms of what I have on the right hand side here. Now once you substitute that, and once you substitute, a few terms may cancel out, you can check that. And also you will realize that actually there is no difference between Roo prime t and Roo prime t plus delta t as far as the observer is concerned. So if you are fixed to this frame F, O is fixed to your frame, O prime is also fixed to your frame. So the vector Roo prime will remain unchanged at all times. Why? Because the frame is a rigid body, right? So the vector O prime O at time t and time t plus t are the same. So if you use this simplification, you will be able to conclude that this expression what I have for V prime Pf is identical to the expression I have for Vpf here. You should do this as a homework. It is a homework exercise I am leaving you with to conclude, to be able to come to this conclusion that V prime Pf is equal to Vpf. Okay, so the choice of origin doesn't matter as far as the origin is fixed to that point. So that concludes our description of what velocity of a particle with respect to a frame is.